This video is going to cover the basics of angular momentum, and it is just the basics. We'll deal with some of the more subtle aspects of it later. Okay, so every time I talk about rotational motion, I say, oh yeah, it's just like linear motion, except things are rotating instead of going from A to B, that there are all these analogs between what we've learned about in linear motion and what the concepts are in terms of rotational motion. And that trend keeps going. So we have basically three ideas in linear momentum. We have the definition of momentum. There's going to be an analog with, there's going to be a corresponding analog that's called angular momentum. We have this idea that impulse changes momentum. Well, there's going to be a rotational analog to that. And then we have this concept of, hey, momentum is conserved, will not change under certain circumstances. And there's going to be an analog to that in the context of rotational motion. Okay, so what is the analog to linear momentum in rotational motion? Okay, don't blame me, but there is this concept of angular momentum, and the symbol for it is capital L, and it is a vector, although I'm going to go ahead and get rid of that because we deal with the vector nature, the directional aspect, with just plus or minus, and that angular momentum is defined similar to momentum, except instead of mass, we have to deal with rotational inertia, or moment of inertia, and that's I. And then instead of velocity, we're going to have angular velocity. And it can be, the direction is simply dealt with by just, hey, is it clockwise or counterclockwise? In which case it would be plus 4 counterclockwise and negative 4 clockwise. And we'll do an example of this later, but that's the idea of angular momentum. The next one is this idea of the impulse momentum theorem, that on the linear side, if something receives an impulse, its momentum will change by that amount. For example, a 50 Newton second impulse would cause a change of momentum of 50 kilogram meters per second. Okay, there is an analogy in the rotational motion side. Now, there's no symbol for angular impulse, but what it is okay, take a torque and then have it act over some time period, and this is angular impulse. No symbol, I'm not sure why, but what would it do? Well, we see over here on the left side that linear impulse causes momentum to change. Well, we're going to see that it's going to cause a change in the angular momentum of the object on which that receives the angular impulse. And so much like I've done here on the left side with F delta T equals M delta V, it's not really anything different. I'm just going to go ahead and write it all out. That what would be the change of momentum, angular momentum? Well, let's just go ahead and write the whole thing down. So a torque acting over a time interval would cause an object with a certain rotational inertia to change its angular velocity by a certain amount. So this would be the angular impulse, angular momentum theorem, I guess. And the last main concept that we introduced in momentum is this idea of conservation of momentum, that if the external forces acting on a system add up to zero, or essentially zero if the time is short enough, then we can say that the momentum of our system before or at the beginning will equal the momentum of our system after, which is generally like after a collision, after an explosion. It could be just the passage of time, but generally there's some kind of an event. Otherwise, we wouldn't really be analyzing it. So let's take a look. What is the analog on the rotational side? Well, you can probably guess. If the sum of, now over here on the left, it was all the external forces. Well, here it's going to be if all of the external torques are 0, then we can say that the angular momentum of our system before something happens is going to equal the angular momentum of our system after. Okay, so this is, you can see, the analogs. All right. Okay, let's look at some examples. In the first example, we're going to look at how do we quantify the angular momentum of some rotating object. And in this case, we're going to take a disk. And if I recall correctly, the moment of inertia of a disk is 1/2 times the mass of the disk times the radius of the disk squared. And that's not correct. Well, let's just pretend it is, because you don't have to memorize those. All right, and so let's make up some numbers here. So M, the mass of the disk, is 5 kilograms. The radius of the disk is 0.5 meters. Omega is 20 radians per second. And what is the moment of inertia? What is the angular momentum? Well, angular momentum is defined to be the moment of inertia times the angular velocity. And so all we have to do is say the moment of inertia is 1/2 times the mass times r squared, all times the angular velocity, and we just plug it in. I don't know if I'm going to calculate it because I don't have a calculator handy. But that's 1/2 times 5 kilograms times the radius squared is 0.5 meters squared times 20 radians per second. So that's 0.25. Okay, I'm not going to calculate it because you can do it. But that's basically what you do. Take the moment of inertia. Take it times, multiply that by the angular velocity. If it's counterclockwise, it's positive. If it's you got it. If it's clockwise, it's negative. That's how you quantify angular momentum. In the next example, we'll look at this angular impulse, angular momentum theorem. I don't think that's its official title, but that's the way it is. I mean, it's basically the analog to the impulse momentum theorem. All right, so here's our example here. I have something like a disc, so think of it like a pulley, and there's some string on it, and if you follow the string, you can see, oh, you're pulling on it, but it's not a constant pull, and your force acting some distance from the axis of rotation results in a torque. And what we see here on this graph is a graph of angular impulse. Well, sorry, the graph is your torque over time, and so the area under the curve would be the angular impulse, and we don't have a symbol for that. And I want to know what would be the angular momentum of the disk after your pull. And then maybe I would want to know, okay, if I know the mass and the radius of the pulley, then I might ask what would be the angular velocity. So we would just say, using the angular impulse, angular momentum theorem, we would say, hey, your torque over time is going to cause a change in the angular momentum of your object. And okay, let's just make this up. So what would be torque over time? So that would be, let's just say it's 100 Newton meter seconds, which looks crazy, but this Newton meters is the unit of torque, and seconds is seconds, and so Newton meters times seconds. So if you had a 100 Newton meter seconds angular impulse, then what would be the change in the angular momentum? And of course, it's going to be, hey, 50 Newton meters of torque. Sorry, well, it wouldn't be, but 50 Newton meter seconds. I know the units are crazy, but 50 on the left side means it's going to be 50, oh my goodness, kilogram meter squared per second. So 50 equals 50. Now, how would I get the if I know, so I know that after the end of your angular impulse, that the angular momentum of this rotating pulley is 50 kilogram meters squared per second. How might I get the angular velocity? Suppose that's what I want to know. Well, you're going to say, go back to your definition of angular impulse. Angular impulse is moment of inertia times angular velocity. So you would rearrange to solve for angular velocity, and that's going to be the angular momentum divided by I, and this is one of those this is a disk thing, so that would be 1/2 mr squared. And if I gave you the mass and I gave you the radius, then you would just plug it in, and that's how you would use the angular impulse, angular momentum theorem to approach a problem. In the last example, we're going to use angular conservation of momentum to solve a particular problem. So there's a little bit of a setup here. So if you look on the left side here, I've got this disk and it's rotating with some initial angular velocity, and I'm going to say it's plus 5 radians per second, plus because it's counterclockwise, and it's doing its thing. It's just there's no torque on it, at least for now. And then a point mass is just simply dropped on top of it, and it lands and goes splat. And then a short while later, we're seeing that this little point mass is sitting on top of the disk, and they're both rotating at some unknown and common angular velocity. And it turns out that the point mass is 0.2 meters away from the axis of rotation. I've also given you, I've just gone ahead and given you the moment of inertia of the disk, 15 kilogram meters squared. And the mass of this point mass is 0.5 kilograms. So let's think about how we could use conservation of momentum to answer this problem. Well, actually, let's think about why we have to use conservation of momentum, how there really isn't any other alternative. Okay, so I have no idea. I have zero information about what torque is acting on the disk when the point mass falls on it, and then there's going to be torque associated with that interaction because the point mass is going to have to speed up. It's going to have to begin to rotate. So the disk is going to exert a torque on the point mass to make it speed up. The point mass is going to exert a counter torque on the rotating disk, which will cause it to slow down. I have no information about any of that torque. I also don't know anything about the impulse that the point mass exerts on the disk, or the corresponding angular impulse that the disk exerts on the point mass to make it begin to rotate. However, if I think about, there's green, if I think about a system involving both the rotating disk and the point mass together, and I say, hey, there's no outside torques, we're going to assume that this thing rotates without friction, then we can use conservation of angular momentum, because yes, there's torque associated with the point mass as it hits the disk, but those are all internal torques. And just like we saw with linear momentum, if there's no outside force, linear momentum is conserved. Here we're going to see that since these torques are internal to our point mass disk system, then the overall angular momentum of my system will not change before, during, after this kind of rotational collision. So let's think about how we would do that. This should have a familiar ring to it. Well, first of all, this part should have a familiar ring too. I'm going to think about, okay, who's number 1 and who's number 2. So I'm going to make the disk, because it's big and it's important, I'm going to make it number 1, and I'm going to make the point mass number 2. Okay, now this is the part that should also look familiar. Maybe not the letters, but the process. Okay, I'm going to have L1 plus L2 equals L1 prime plus L2 prime. And I can only say that if the sum of all those external torques equals 0, and it is true, So really, there's no if. They are 0, so this is our statement of conservation of angular momentum. And it looks a lot like how we approach our linear momentum. Now, what would be the angular momentum of the different pieces of my system? Well, L1 becomes I1 omega 1, and the angular momentum of the second object is I2 times omega 2. And you can see I'm just doing the same thing here. This would be I1 omega 1 prime plus I2 omega 2 prime. And so just like in conservation of momentum problems before, I want to kind of customize it to see what am I being asked to solve for? What can I simplify? The first thing I'm going to say is that the point mass, until it hits the table, this is as it's falling, or even before it's released, it has no angular momentum. It's not rotating, so that's 0. The next thing I want to think about is, well, here's the left side. The next thing I want to think about is, hey, this point mass, this is my point mass term, this is the disk, they're rotating at the same amount. So we're going to say that omega 1 prime is the same as omega 2 prime. There is no difference, so we're just going to call that omega prime. And this is what we're after, actually. I want to know what the angular velocity of the disk is after that point mass is dropped onto it. So I'm going to just simplify this and say, look, I've got I1 plus I2. These are their combined moments of inertia. I'm going to multiply that by omega prime. And that, again, that's what I'm after, this guy right here. And if you think about it, I know everything. Well, there's one subtlety here that we'll have to get into. But basically, I'm just going to go ahead and solve for omega prime. And so what do I get? I get I1 over I1 plus I2 all times the original omega. Now, what's the one subtlety? I'm actually given the moment of inertia of the disk, so that would just go in here and here. But I'm not given the moment of inertia of a point mass. And again, if you may recall, this is the one that you need to memorize. So the moment of inertia of a point mass is going to be mr squared. And I'm running out of time. Now let's go ahead and put the numbers in. You can always stop watching the video when you want. Okay, so I2 is going to be mr squared. Okay, let's go ahead and just put the numbers in for that. Okay, so what is I2 then? All right, its mass is 0.5 kilograms and R is 0.2 meters. So 0.5 kilograms, 0.2 meters. So we've got 0.5 kilograms times 0.2 meters squared. 0.5 times 0.04. That seems to me that's going to be like 0.2. If I'm wrong, don't worry about it. Okay, I'm just going to say that's what it is. I think that's what it is. Okay, so now that was the one subtlety, is I was not given the moment of inertia of this point mass. But now I can solve for it of our final angular velocity. Okay, so I take the moment of inertia of the disk, that's 15. I'm going to skip the units for now because just to shorten the video. Okay, so that's the top. Then on the bottom, I take the moment of inertia of the disk plus the moment of inertia of the point mass. And you can see it's not going to slow down by very much. This angular velocity is going to be about the same. So there you go. It's going to be 15 over 15.2. Okay, the units would have canceled out, and the initial angular velocity is 5 radians per second. And you can see my stupid surface it's getting too hot, and then when it gets too hot, you can see that the screen is jiggling. So I think I'm going to be done here. Anyway, that's the basic intro to conservation of angular momentum.